वीर्यं करवावहै तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
So, we have been discussing about the different processing steps used in fabricating a bipolar junction transistor in integrated circuit. We have started with an NPN transistor. We have seen how the isolation between the transistors have to be obtained either by junction isolation or by dielectric isolation. In dielectric isolation, you have also seen low cost as well as trench isolation, and then we have said that it can even be done by using selective epitaxy. After the isolation comes the base doping step, and there also we have outlined the basic strategy, that is depending on the junction depth we use either diffusion or ion implantation, and in the extreme case of very shallow base junction we have to use a poly base, that is in that case we first deposit an undoped poly, implant in that poly taking care that no implantation goes into the crystalline silicon, and afterwards using this implanted poly as the dopant source we do a short thermal anneal and we create a very shallow base. Now, please understand that this strategy is as far as the active base is concerned. Now, what do I mean by the active base? What I mean is simply this: I have this transistor, started from a p-type substrate, had the N plus buried layer, then I have the N epitaxial layer. I can have some kind of an isolation, either junction or oxide. Let us say I have oxide isolation here. And then I have the P base region, and then I have the emitter. So, this N plus Pn is actually my transistor, right. So, what is the active base? Active base is actually this, the P region directly underneath the emitter. This is my active base. Agreed? This is the path of the current. This is the active base. So, what about this portion of the base? In the active base, in order to keep the beta of the transistor high, I must have a low Gummel number, that is the base doping must be low, but not too low so that there is no punch through. Okay. Keeping that in mind, I must keep the Gummel number as small as possible so as to have the high beta of the transistor. But what is the requirement in the rest of the portion, which is called the extrinsic base, right. So, we have active base and extrinsic base. The extrinsic base is needed only to provide the base contact. So, the P region surrounding the emitter is the extrinsic base, and that must be doped high to provide a low resistance path to the active base, because you see your base contact is taken from here. So, when you are injecting a base current, the current must flow like this and go into the active base, right. So, you do not want unnecessary voltage drop in the extrinsic base. That means, you want the extrinsic base to be as highly doped as possible in order to cut down the voltage drop in this region. Yes? So, what we do is, we use our strategies which we have discussed already for the active base, and in order to have a high doping in the extrinsic base, we have to do something else. How do we keep the extrinsic base resistance low? By making it highly doped. And this, that is the dual requirement, that of high doping in the extrinsic base and low doping in the active base, can be achieved either by using a double implantation or by using a single implantation. How? Let us see. Suppose what I am trying to plot is the doping concentration with the distance. Okay. Now, let us say I use an implantation like this for the base region, an implantation profile like this for the base region, okay. And let us say my emitter doping is going to be the dotted line is for the emitter, the solid line is for the base, right. Then as far as the active base is concerned, active base is directly beneath the emitter, directly below the emitter. As far as the active base is concerned, this is the profile in the active base, right. I have only a small total charge in the active base region. However, as far as the extrinsic base is concerned, I see a much higher total charge with higher surface concentration. That is, the region surrounding the emitter has the full benefit of this implantation profile, and it has a much higher doping concentration and therefore much lower resistivity. Clear? I can of course get the same thing by doing a double implantation also, and the advantage in the double implantation will be that it will give me a better control. Okay. In that case, what do we do? That is to say, I use two implantation for the base. This is for the extrinsic base and this is for the active base, and this is my emitter implantation. I adjust the base implantation depth such that the extrinsic base implantation depth coincides with the emitter, and I have a second base implantation in order to obtain my active base. So, this is actually the active phase. Immediately below the emitter, whereas as far as the extrinsic base is concerned, you are getting the full benefit of the doping concentration. This of course will give you a better control over the base depth as well as over the base doping concentration. So, please understand that in integrated circuit, along with the active base, it is very important to have the doping concentration of the extrinsic base also properly designed. The extrinsic base must be highly doped in order to cut down the resistive drop in that region, parasitic drop in that region, and therefore, the base implantation has to take into account both the requirements for the active base as well as for the extrinsic base. This can be achieved by suitably tailoring the doping profile either by using a single implantation or by using a double implantation, one implantation for active region, the other implantation for the extrinsic region. Okay. So, this is as far as the base doping is concerned. Next step is of course the emitter doping, and even in emitter doping we simply go by the junction depth requirements so as to decide whether we use diffusion or ion implantation to realize the emitter. And even in that case, you know, the same thumb rule holds good, that is, if the junction depth is greater than equal to 0.5 micron, you can do it either by diffusion or by ion implantation. For diffusion we mostly use phosphorus, okay, because you could use arsenic, but arsenic has out diffusion problem. So, the maximum surface concentration achievable is not as high as in case of phosphorus. So, mostly we use phosphorus, which also diffuse faster. If your junction depth is less than 0.5 micron, mostly we use implantation, and for implantation arsenic is preferred, implant arsenic. If your junction depth requirement is much less than 0.5 micron, then just like in case of base, even here you use a doped poly as the source, that is, on emitter you deposit poly, you implant N plus arsenic in it, and then from that you do a short thermal anneal to realize a very shallow emitter. Okay. For shallow junctions, obviously we prefer arsenic because arsenic has a lower diffusion coefficient, it will give you a shallower junction. Okay. Now, this is basically the NPN transistor with no special requirements. This is an NPN transistor with no specific requirements or specifications. The problems we may have in this case are, of course, you know, if you use phosphorus as the emitter, you can have an emitter push effect which will widen the base and therefore reduce the beta of the transistor. If you use aluminum as the metal contact, you can have aluminum spiking the junction, particularly when your junction depths are narrow. When we are talking about shallow base, you can have junction spiking, you can also have electromigration problem. And if there is localized enhanced diffusion, then you can have an emitter collector pipe, that is, if there is an enhanced diffusion like this, emitter and collector getting shorted. So, these are the three basic yield problems as far as an NPN bipolar junction transistor is concerned. You have an emitter collector pipe due to enhanced localized diffusion. You can have a base widening effect because of emitter push if you use phosphorus as emitter, and you can also have junction spiking, particularly when we are talking about shallow base. Aluminum could spike the junction unless you have taken proper precaution by using an alloy which contains silicon along with aluminum. Okay. So, you see, so far we are discussing only about NPN transistor. NPN transistor have some specific merits as far as integrated circuit technology is concerned. Some of them are like, you can have a higher emitter doping concentration if you use N emitter rather than if you use P. Then you can have better facility of making ohmic contacts. It is more difficult to make ohmic contact to moderately doped N region. So, if you have a PNP transistor where your base is moderately doped, you will have difficulty in forming an ohmic contact. In NPN transistor, there are no such problems, but still for some specific applications, particularly in case of analog devices, we use PNP transistors as well as NPN transistors. Okay. So, how does one fabricate a PNP transistor? Or more importantly, I have an already established NPN transistor process flow. So, how do I use this same process flow, add maybe 1 or 2 more steps and realize a PNP transistor in the same NPN transistor process flow? Okay. So, let us try to realize a PNP transistor in an NPN process flow. Essentially, this is my NPN transistor, NPN, right. Keeping this basic process flow intact, if I want to realize a PNP transistor, I have 2 possibilities, 2 choices. That is, I keep the NPN transistor process flow as it is and use one extra P diffusion, so that I get this PNP transistor. This is easy to say, but very difficult to achieve. You see, realizing an NPN transistor by double diffusion process itself is quite tricky, because you are going to use 2 subsequent diffusions, one after another. One for the base of the NPN transistor, the other for the emitter of the NPN transistor. Now, the process we are talking about is a 3 diffusion process. You have another P diffusion, and notice, remember that diffusion means this is the highest surface concentration, then this, then this, then this. So, it is going to be extremely difficult to realize a PNP transistor by this 3 successive diffusion process. Okay. So, even though this is a possible solution, this is not really feasible. What is the other possibility? I could use this PNP transistor, that is, I could use the base collector substrate PNP transistor, base collector substrate PNP transistor, right. I have already one PNP transistor integrated in this NPN process flow. I could try to use this PNP transistor, that is, I am going to use the substrate as the collector of the PNP transistor. But this will create a major problem, because you see your substrate is lowest doped, you will have a very high collector resistance, and on top of that you have the N plus buried layer, okay, which is going to be in the base of this PNP transistor. So, essentially this is going to cut down the gain of the PNP transistor, because you are increasing the total charge in the base, you are increasing the Gummel number. right. So, both these avenues seem to be not quite feasible. In other words, if I want to realize a vertical PNP transistor, that is emitter on top, base under that and collector under that, current flow is in the vertical direction. If I want to realize a vertical PNP transistor, I am going to have problems. So, the remedy is, let us try to use a lateral PNP transistor. In a lateral PNP transistor, I have the emitter surrounded by the collectors and the current flow is, this is P, this is N, this is P, PNP transistor. So, the current flow is no longer in the vertical direction, it is in the lateral direction, and that is why this transistor is called a lateral PNP transistor. Okay. Now, look at this transistor very carefully. What do I have? I have this collector P, then I have this base N, okay, let us say this is the emitter P and this is the collector P. Okay. Base is N, emitter is P, collector is P. Now, look that there is another PNP transistor also available in the same diagram. What is that PNP transistor? One is collector, base, substrate, emitter, base, substrate. In both cases the bases are common. So, I have this base, I can think that the substrate is grounded. At the same time, I have right. I have this lateral PNP transistor as my main transistor. This is my main transistor PNP, but using the collector of this PNP transistor, the base of the PNP transistor and the substrate as the P, I can have another PNP transistor. Similarly, using the emitter, base and the substrate, I have another PNP transistor. All of them share the same base. Agreed? So, you see, every lateral PNP transistor is going to have two parasitic PNP transistors associated with this. However, if you look at this parasitic PNP transistor, its gain is very low because of the N plus buried layer. Because of the presence of the N plus buried layer, which is the base of this PNP transistor, the gain of these parasitic transistors are going to be very small, and therefore, it is not going to affect your actual PNP transistor performance to a large extent. So, this lateral PNP transistor is a feasible design, and in fact, in almost all integrated circuit bipolar junction transistor, PNP transistor is always a lateral transistor, while NPN transistor is a vertical transistor. Because you want to incorporate a PNP transistor in the same process flow as the NPN transistor, and this can only be done, as you have just seen, if we use a lateral design. Then we do not have to change the substrate, we do not have to change the process flow. Simply by having another mask for the PNP transistor, we can realize the lateral PNP transistor. Okay. Now, even though PNP transistor is mostly used for analog circuits, we use PNP or rather a combination of PNP and NPN transistor in digital logic design also for a particular type of logic circuits called the I square L circuits. I square L, integrated injection logic, IIL, integrated injection logic, IIL commonly referred to as I square L circuits. Okay. And what I have here is the basic I square L circuit. Let us see how this circuit is going to perform. What do I have? I have a PNP transistor and an NPN transistor. This PNP transistor is being used as a current source, it's injecting a current. So, from there comes the term injection logic. The same injection current is being given to all the blocks. Okay, I have one block here, this is one block, this is another block, this is another block, right? That is TA and this PNP transistor is one block, TB and this injection logic is another block, TC and this injection current is another block. All the three blocks are identical. Do you see? Okay. Now, let us see how this circuit is going to perform. I have two inputs X and Y. Let us say both X and Y are 0, are at logic level 0. In that case, both TB and TC are cut off, right? X and Y are given at the base of TB and TC. If they are both at logic level 0, then both TB and TC are cut off. In that case, the current here has only one path to flow, that is in the transistor TA, right? And then what is going to happen to the output voltage? What is the output voltage in that case? The output voltage is simply the base emitter drop of this forward biased diode. TA is an NPN transistor, right? So, this is only the base emitter drop of the forward biased diode. How much is that? 0.7 volts. So, when X is 0 and Y is 0, V output is 0.7. Right? Now, suppose X is 1, X is 1, Y is 0. X is 1, that means this transistor is in saturation, TB is in saturation. Okay. So, then what is the output voltage? This output is connected to the collector of TB and therefore V0, and look that the emitter of TB is grounded. So, actually V0 is nothing but the collector emitter voltage of a saturated transistor, of a transistor in saturation, or V0 is nothing but VCE sat. What is VCE sat? 0.2. Identical is the case if X is 0 but Y is 1, In that case, Tc will be in saturation and V0 will still be the collector emitter voltage of a transistor in saturation, Vc is at. And even when both X and Y are 1, so you see, I could say therefore that the output voltage V0 is going to be high only when both the inputs are low, and the output is going to be low when any one or both the inputs are in the high state. In other words, the basic I square L circuit is a NOR gate. 0 0 it is 1, in all other cases it is going to be 0. So, this is basically a NOR gate. Okay. Now, there are several advantages of this I square L circuit. What are these advantages? The advantages are that, first of all, it has very low power dissipation. Okay. It has low power dissipation. That is the first major advantage of I square L, it has low power dissipation. And there is another advantage which will be evident to you if you look at, just concentrate on one building block. Let me rub off all the other extraneous matter and just concentrate on this one building block. This building block is replicated any number of times in the I square L, right. So, let me just concentrate on this one building block. What do you see? I have a PNP transistor and an NPN transistor, right. Okay. Now, let us look at this PNP transistor. Its base is N type and it is grounded, and I have an NPN transistor whose emitter is N type and is also grounded. So, I could use the same N region both for the base of the PNP transistor as well as for the emitter of the NPN transistor. Agreed? See another very interesting thing. The collector of the PNP transistor is fed to the base of the NPN transistor. That is, the collector of the PNP transistor is shorted to the base of the NPN transistor. So, again I could use the same P region for the collector of the PNP transistor as well as for the base of the NPN transistor. In other words, these two transistors are going to share certain regions. These two transistors are not going to be two distinct entities, they are going to share certain regions, or in other words, these two transistors will be merged. I will have a composite structure in which two transistors will be merged together, which gives I square L its other name called NPTEL, merged transistor logic, merged transistor logic. So, obviously, since these two transistors need not be unique entities, but they can share certain regions, packing density of I square L circuit is going to be very high. So, I have the second advantage, it has high packing density. These are the two great advantages of the I square L circuit. One is low power dissipation, the other is high packing density. Okay, now let us look at the basic I square L circuit from the technological point of view. I have started with a substrate called N on N plus, right, that is I have N plus as the bottom layer on which an N epitaxial layer is grown. I have used this N on N plus epitaxial substrate. Okay. Now, in this I have diffused two p regions, right. So, you see I have a lateral PNP transistor, PNP. This is going to be my current source. Okay. In the other p region, I have diffused multiple n plus regions. I have shown only two here, it could be multiple regions. Okay. So, now what is it? Let us see, this is a PNP transistor, okay. And you see this PNP transistor's base is shared with the emitter of the NPN transistor. So, this must be the emitter of the NPN transistor, which should be permanently grounded. Base of the PNP transistor as well as the emitter of the NPN transistor is permanently grounded. Okay. And you see the collector of this PNP transistor is also the base of the NPN transistor, and both purposes are being catered to by this P region. So, this is my PNP transistor and this is my NPN transistor. The interesting point here is that you find that these are the collectors of the NPN transistor and this is the emitter of the NPN transistor, which is actually the inverse of the NPN transistor designs we have done so far. In other words, the NPN transistor in this I square L is operating in the inverted mode, and that gives rise to the disadvantage in the I square L circuit, that is, since the NPN transistor is operating in inverted mode, you have low speed. So, while the first two are the positive features, this is the negative feature of the circuit. Okay. Now, from the technological point of view, I square L circuits have another advantage, that is, in these circuits basically you do not need any isolation. Why? Because remember, all the blocks, whatever I drew here, all the blocks, they had grounded base for PNP transistor and grounded emitter for NPN transistors. Therefore, I do not have to isolate them, they can all share the same substrate. The substrate can be grounded and all the transistors can share that same substrate. So, strictly speaking, in I square L, an isolation is not necessary, right? You do not really have to have an isolation. But of course, in order to make the circuit perform in a more efficient manner, you can use two N plus regions called the N plus collars on both sides of the P diffusion. Okay. This is simply done in order to facilitate hole injection. You see, you are injecting current, right? You want the hole injection in this direction, P and P, you want the hole injection in this direction. Okay. However, as far as holes are concerned, it does not see any difference between this direction or this direction. However, if you add this N plus collar, then because the doping concentration in these regions are going to be far more than in this region, the hole injection will be predominantly in the active direction, in the direction you want it. So, adding N plus collars will actually facilitate hole injection, and that is why usually N plus collars are added in the I square L circuit, though for the basic circuit performance you do not really need to have any isolation. Okay. And of course, as you have seen in case of junction isolation compared to dielectric isolation, if instead of junction isolation we have dielectric isolation, it is always better. So, a more advanced I square L design will be to replace the N plus collars by an oxide. So, in that case we will have a circuit like this. Notice the advantage, I can have my P regions stacked against the oxide as well as my N regions stacked against the oxide. In this particular case, these N plus regions must be separated from the N plus collar, okay. But in this case I do not have any such requirement because I am using an insulator for the isolation, okay. If we look at the top view of these two I square L designs, that is one using N plus collar and the other using the oxide isolation, the difference will be clearer to you. Let us first talk about the top view of the mask, okay, where I use the N plus collar. I have, this is the active region and I have N plus collars surrounding this active region. This is my N plus collar, okay, right. And in this active region I have the consecutive PNP regions. So, this is my P, then this is my N, this is my P, in which I have this N plus regions, right. Remember, I must have a contact here. This is my output point. I must have a contact here. So, I should have a contact for base in this region. Okay? So, this is the N plus collar, this is my PNP transistor and this is my NPN transistor. If I compare it with the oxide isolation case, it is surrounded by the oxide and I have this P region here, this N region here. Now, my N region can extend all the way up to the oxide, whereas in this case they must be separated from the N plus collar by the intervening P region. Do you understand the basic difference? Here I can stack the N plus layer directly against the oxide, but in this case I must have a separation from the N plus collar by this P region. So, this is actually called the rails. On both sides the region that we have is called the rails. So, as is obvious, if you compare these two mask designs, I have a lot of space saving if we use an oxide isolation. Just compare this with this. I can achieve the same using a much smaller region. See, finally everything is determined by your lithographic limitation. So, it depends on how small an N plus region you can have. Here you must have a separation. Here you do not need to have a separation. Therefore, the dimensions of this can be much smaller than in this case. But even though space saving is a great advantage, the oxide isolation case does have a small problem. And what is that small problem? Look at the way the current flows from the base to this. I have to have multiple collector in the I square L. Multiple collector means I have so many fan outs. Okay. So, the path of the current in this case is like this. Current can flow through the rails. I have P regions on both sides which are the rails, and the current can flow, go to the second collector, to the third collector through the rails. In this case, however, how will the current flow? From this base to this first collector, it is not a problem. How about the second collector? It must flow underneath the first collector in order to reach the second collector, because I do not have any space on both sides for the current to flow, right. So, here it is like this. In the next case it is going to be like this. The dotted line signifies that the current is flowing under the first collector in order to reach the second collector. And if I have a third collector, current has to flow underneath the first two collectors to reach the third collector. And whenever I have the current flowing underneath the collector, I am making it flow through a constricted region, and therefore, the resistance in that path is going to be larger. So, I will have unequal voltage drops, and which will lead to unequal drives. Remember, the multiple collectors actually represent the multiple fan outs. So, different fan outs will receive different drives. Okay? So, this is the problem in the oxide isolation case. By removing this rails, which I thought was the unwanted region, by removing these additional P regions, we have indeed saved a lot of space, but in the process we are having unequal drives. So, what is the solution? The solution is to have multiple base contacts. One base contact here, another base contact here, another base contact here, so that the current in all cases they flow through equal resistance paths. Okay? Instead of having one base contact, you have one contact here, one contact here, one contact here, all of them are tied together to have the carbon base. This requirement of having multiple base contacts actually leads to a self-aligned I square L structure, which we will discuss in tomorrow's class.